This lecture is about cache memories, and they are essential for high performance computers. Without cache memories, all computers would look terribly slow. What is a cache memory? It's a smaller and faster memory where popular data items are stored. Cache memories are used in daily life as well. For instance, we have a refrigerator where popular food items are put. We don't order food or go to a supermarket whenever we need something to eat. Another example is a cache in your web browser. So everyone uses caches already, and now this lecture will explain how they are made in computers. Okay. So, in general, there is a trade-off between the speed and size of memories. So either it is fast and small or big and slow as a basic rule, or some kind of compromise. As programmers, we want, of course, fast and big memories, and it should take one clock cycle or the equivalent of doing an arithmetic instruction to fetch memory to fetch data from memory, and it should be huge. Okay, that will be nice, but that's not possible, at least not affordable. So what is needed is some kind of trick to make this work. Reading from normal raw memories can take hundreds of clock cycles. Okay, so in general, when a computer engineering problem should be solved, I mean a research problem, not why the display doesn't work, to come up with an invention of how to change something so that it will work better in some sense, we need to observe what actually happens and try to make generalizations so that we can exploit what is happening. That is, observing phenomena and then change the design of the computer to exploit this. Okay, and there are two important observations that can be made from how computer programs usually use memory. Okay, and there is one general term, and it's called locality, and that is divided into two separate items or kinds of locality. First, temporal locality. It means that if we access a memory location A, then it's likely that we will soon access it again. Okay, that's fine, and it sounds reasonable. For say we have a loop index variable, usually we use this I in each iteration. Okay, or the another observation that is made is spatial locality. And that means if we use address A, then it's likely that we will also access A plus 1. And how come? Well, there are different situations, but if we iterate through an array, for instance, then we have spatial locality. So these localities, it is behavior that is very, very frequent in computer programs. Without locality, then cache memories would not be very useful. Okay, so if we have say we have an array and we traverse it one element at a time, then we can exploit spatial locality. But if we use this array as a hash table, then the elements are more or less randomly. I mean, that's the goal, to avoid collisions in the hash table, that we should spread out the elements as much as possible. Such code has less spatial locality. Okay, so examples of temporal locality: instructions in a loop. They will be used next iteration as well. That one I already mentioned. Stack space. When we make one function call and return and then make another, we will reuse the memory that the previous function was used. And if we have some kind of object or a struct, then usually it's accessed several times, and then we do something else. Spatial locality: the instructions are usually executed one after another until we branch. And often there are several variables in an object, and if we know which ones are accessed more or less at the same time, then we can declare them in the struct and near each other, so that they will exhibit spatial locality when we access them. So, how can we create hardware that can exploit temporal locality? It's quite easy. This struct is an extension to the CPU that you saw earlier in the file machine.c. The file machine.c had the CPU with only this array of registers and a program counter. Now we add a cache array. This is a very small cache, but that's fine for illustration. Okay, so what can we do with this? In each element in this array is a struct, and it contains data and address and a boolean which says if this data and address are valid or not. Okay, so what we can do is to put the 8 most popular data items in this cache array. And to know which data we have, we clearly need to know which address it was. So when we want to data from, instead of reading it from memory, we can check if the address is the address that we wanted to read from memory. Okay, so where do the addresses come from? If we have a global variable x, and who decides which address it should be at? Well, it's the compiler. And say it decided that this variable should be at the address 293, or hex like that, or binary like that. Then we should figure out where to put this variable x in the cache memory. And one way to do that is to take the lower bits here to decide where to put it. Okay, so recall, we had an array with 8 bytes. So what we can do is to take these 3 bits and use them as an index into the array. So okay, so how many indices can we use? It's 3 bits, so it's 2 to the power of 3 equals 8, and well, this is quite obvious, and we can just use this and check if the rest of the bits, I mean all of the bits, this value is in this variable. For it was 5, for index, I mean for CPU, and I just write cache. No, I can be more appropriate and write of 5. And then we check if this one is equal to 293. In that case, we should also check if valid is true, and then we can get this data. That's the basic idea with cache memories. If we find that this is that they match, then we say that we have a cache hit. If it don't match, then we have a cache miss. And programs with many cache hits, like over 90%, significantly over 90%, they are really much faster than those which don't have cache hits. Each time we can save 100 clock cycles, for instance, or more, depending on which kind of machine it is. So let's look. First of all, there is a for loop. Okay, this is the load instruction from machine.c. And what we want to do is to read the data from memory, but before accessing it from memory, we try to find it in the cache. Okay, and in C code, this is a simple loop, but in hardware, this loop is not executed in sequence, but instead all iterations are done at the same time. So this is very important, because a common way to get to lose points at the exam is to answer that doing this loop takes a lot of time, but there is no loop. Okay, so that's why I am writing this as clear as I can. Okay, so what we do is, first of all, we check if this array is valid, I mean the element, and if the address match. In that case, we fetch the data and say we found it, and skip this loop, which doesn't exist.